and the cyan vertices are sort of scattered around the periphery. So these are four sort of stylized versions of large-scale structure, all of which can be compactly represented inside the stochastic block model. So when we apply it to real data, if we give the model something like this, we hope to get out some structure like this, and that gives us a way of understanding what we have just seen. OK. So let's do some math. I like math, too. I like statistics. Funny story, I've never taken a statistics course. Turns out that you can learn a lot just by messing around with data. So how do we actually learn one of these models from real data? Well, we have to have some graph G, and that defines a set of edges and a set of things that aren't connected. So the probability of generating exactly a graph G, given that I have some labeling on the vertices and some mixing matrix, is two parts. One is the probability of generating all the edges. So for each ij that is an edge, the probability that edge exists is just given by the element of the matrix that corresponds to the colors, the pair of colors on that edge. And then the probability that all the things that don't exist is 1 minus that probability for all the edges that don't exist. So this is the probability of generating exactly this set of edges and not any other set of edges. Or more generally, if you don't like this sort of simple graph representation in which edges either exist or don't exist, or if you don't like having perhaps a labeling here, we can represent it more generally by saying that there's just some function that tells us the probability here. It tells the probability that aij is a 1 or a 0 or some other value. It could be 3, 4, 5, a real value, et cetera. And it depends on some parameters that we look up in some large structure. So in the stochastic block model up here, this R is that matrix. But it doesn't have to be a matrix. It could be any partition of the pairs, and it still works. You just have to have a unique element inside that structure that corresponds to the probability that I and j are connected. So if we change f, for instance, we can get lots of different kinds of graphs. We can get simple graphs. That's this thing up here, in which the outcome is a 1 or a 0. If it's a